Hi everyone to another lecture of Physics Latam. Today we have the final lecture of Professor Miles Reid. Please go ahead.
Yes, so compared to the first three lectures, this material is speculative. So, I don't have anything more to say that I know, but I have a lot of things that I guess. Yes, so in particular, I gave you a method of constructing a space that I assert is a projective homogeneous space for the Lie group E6. And, if you don't know what E6 is, which I don't really, E6 can be thought of as the group of symmetries of that projective homogeneous space. So, it's known in the literature as the complexified projective plane over the octonions. But, that's a pretty complicated thing to describe. And saying it's the symmetry group of something doesn't tell you any of its elements. Yeah. Anyway, now I want to take this E6 and divide it by 2 to get a different Lie group F4. Yeah. So, F4 is certainly not the hardest of these groups, but I don't really know what it is at all. Yeah. So I say, look at WE6. So I described that last time. This is a permutation group of 27 elements. It's got 51,840 elements. It was studied by about 100 mathematicians in the 19th century, right? If you want to work with a group of that size, you normally use computer algebra. Yes? So I'm looking at involution. So an involution is a group order of 2, order 2. So it's like mirror, like reflection in the mirror, or so I want to take something in WE6, an element of the symmetry group of E6 of order 2, and I want to say that F4 is the one of the fixed locuses of this symmetry. Yes, so last time I had this notation. If you want to give names to all the lines on the cubic surface, this is one map. This is the map that preserves 6 factorial symmetries, 720 symmetries. Yeah, so there are 36 of these Schliffli double sixes, or 72 of them if you think of the horizontal and vertical as being separate. Yes, so those are the 27 lines. So I'm yeah, okay. I had a student visit at that time. So I'm going to take one particular double six, right? I'm taking the symmetry that swaps the L1 and the N1 and then behaves, as I say here, on all the other lines. Yes? So, so I told you, I gave you notation for the root system last time, and I hope I've got the right one. I'm just take the picture of the Deakin diagram of E6. It's, yes? And I'm going to look at the natural symmetry of that root system. So, the line along the bottom is 5 generators of symmetric group on 5 elements. Sorry, symmetric group on 6 elements. And L1 to L6, L2 to L5, L3 to L4 is just that symmetry. Yes? So now I'm taking, this is a different involution. I'm sorry, I'm screwed up a bit there. So what I'm going to do is fix the lines of one particular triangle and swap over all the lines in line pairs meeting them. So L1 meets the 5 Ni and it meets the 4 Ni and it meets the 4 M1I. Yeah, for I not equal to 1 and 6, and then the same. So, this is sort of basically just sitting down and playing around with permutation. I did it in computer algebra, but I can't show you the computer algebra without stopping sharing and starting sharing. Anyway, in a group, if I've got one element, I can ask for all the elements that commute with that. Yes, so you ask the computer to calculate that centralizer, and it is the bioloop of F4. Yes, so I believe that this is the homogeneous space I talked about yesterday, and I'm saying alleged because I haven't actually proved it, and for pure mathematicians, as opposed to physicists, proof is more important than understanding. Yes, so I've got this V16, which I want to think of as being something like a Grassmannian variety that E6 acts on, and E6 is the symmetry of V16. And then I take this involution, I'm taking the variety and folding it in half, and then there is the line of folds, which is the fixed locus. So when a group 42 acts on 23, in 27 coordinates, the most likely thing is that there are 23 pluses and 24 minuses. So there are 2 different fixed locuses, and I hope, I assert, I conjecture, if you like, to use the technical mathematical term, that one of these is a symmetric space, a projective homogeneous space for F4. Okay, now how do I answer that? Yes, so the involution also acts on the root system. So I told you the names for my roots. And so E1 was this one, 1 minus 1, 0, 0, 0, right? And E5 was this last one. So if I take the sum of the two, I get this, yes? And then the same with the others. So these form a four-dimensional subspace of the Lorentz space L7. These are points in a real vector space, but the real vector space has an integer lattice, a lattice of integer points. Yes? So because I've done plus or minus one symmetry, I need to take 1/2. So these vectors here have length probably 4. You calculate the length of them according to that Lorentz metric I gave you last time. So I'm taking 1/2 of the restriction. This is a standard mathematical trick. Right, so the intersection of these elements is this matrix. And that is the Lehi diagram F4. Yes? And the I verify by straightforward calculation. This would be quite easy to do by hand, but it's, you know, once you've started doing it, you continue doing computer algebra, and you believe the computer more than you believe your own calculation. Yes, and so that's the combinatorics of F4 sorted out. So, you know, in principle, it's a straightforward exercise to calculate the fixed velocities and to calculate the subgroup of E6, which is invariant under this involution, right? So this is homework that I have not yet done. Yeah, so I've finished talking about this section 1. Yes, so in that first section about F4, I was taking E6 and I was dividing it by its left to right symmetry of order 2. Here I'm doing something different. Here I'm chopping bits off it. So if I take E6, E6 contains this thing, D5, as a subgraph, and it contains this one also as a subgraph. Now, this value of A5 is the symmetry root of GL5. So, you know, when I was doing GL5, I gave you Rashmanian 2-5, and I said, write 2 by 5 matrices. And the value of that is just interchanging row 1 and 2, column 1 and 2, column 2 and 3, column, and so on, and that generates the Coxeter group in this diagram, which is the simplest possible Coxeter group, it's the group SIM5, the symmetric group on 5 elements. So if you've done a course in group theory, you will have seen algebraists telling you that the alternating group on 5 elements is a simple group. Yes? So now I want to say, let's, when I did E6, I had the cubic surface. When I did D5, I had the del Pezzo surface of degree 4, which is the intersection of 2 quadrates. And I claimed to construct the combinatorics of the groups and the homogeneous symmetric spaces of the groups in terms of that combinatorics. So this is a really beautiful exercise. So Rachmaninoff 2-5. Yes, so I told you one treatment of it last in the first lecture, and it's this 2x5 matrix, and that has this 5-fold symmetry. And then I told you that we're going to take the 2x2 minus of that and use it to embed Gras 2-5 into P10. Yes? And now I'm giving you a completely different way of thinking about this. Yes? The del Pezzo surface of degree 5 in P5 is what you get if you blow up 4 points in P2. So if you got 4 points in P2, you can draw the 4 lines drawing any pair, and you get the complete quadrilateral. Yes? And there is also that has, if you blow up those lines, you get 1 minus 1 vector. This is the same as on DP5 and DP3 that I discussed in the subsequent lectures. You get these 5. I'm drawing here some kind of pictorial representation of a surface having 10 lines, and it's a kind of dual representation. The lines are the nodes, and 2 lines intersect if they're joined by an edge of the graph. Yes, so this is a famous graph. It has symmetry Rachmaninoff 2-5. Right, and I can write its nodes as a 5x5 skew matrix. And this has the property that A1 multiplies A2, and A2 multiplies A3, A3 multiplies A4, and A4 multiplies A5, and A5 multiplies A1. Yes, so when I make Pfaffians, remember the formula for a Pfaffian is entry 1, 2 times 3, 4 minus 1 entry 1, 3 times 2, 4, and then plus entry, the other one, whatever I said, 1, 4, 2, 3. Yes, and so these are the 5 Pfaffians. And all of this comes in a completely transparent way from the famous Peterson graph. The graph is always drawn in this way by combinatorians, right? Because they like thinking in 2 dimensions. It's a much more adult point of view to think of the diagram being in perspective. In other words, lift the middle pentagram out of the page so that it's really the same size as the big pentagram. Yes, then these lines A1, A2 become columns of a cylinder, and then the roof of the building doesn't have a pentagon in it, has a pentagram instead. Yes, so this Peterson graph is completely determined by the root system of A4 and the violet has that amount of symmetry. Yes, so it doesn't have top to bottom symmetry. There is no symmetry that swaps the A's and the B's. And if you're a mathematician and you see this, you spend half an hour trying to get rid of the minus signs. And it's a proverb that I think goes back to Elie Castor, who invented one of the inventors of Lie algebra around 1890, that you can never get rid of the minus sign. Yes, so if you move a minus sign, if you change a minus sign to a plus, then 2 other pluses will change to minus. Yeah, but as I said, the A's and the B's are not symmetric. That's the graphic representation of the Peterson graph tells you that. Yeah. So I'm just saying the same thing again. So if you do Pfaffians, you only multiply these antisymmetric elements with guys that are not in the same row or same column. Right, so this guy here, this is a skew matrix with minus A1 there. So A1 is in the same row as B5, B4, A3, and it's in the same column as A4, B3, B2. Right, so it's only Pfaffian partners are A1, B1, and A1, A2, and A1, A5. Okay, so, who does A multiply in this set of equations? Set of equation has 15 edges. Each edge has 3 vertices. They're the Pfaffians and so on. Okay, so let me go on. So I told you I could take this graph and chop off 1 edge and then chop off 2 edges. So why don't I chop off 1 edge there and 1 edge there? Then I get D4. So, the stuff I told you about Pfaffians was long-winded and basically all trivial. The material here is completely non-trivial. So things happen in dimension 7 and 8. Yes, so in dimension 8, you have the algebra of octonions, which is not associative. So, if you're a physicist, you will probably enjoy reading John Byers' essay on octonions. So he tells you everything in spinor theory or Bott periodicity and so on comes from the octonions. So, a few decades ago, physicists, particle physics, high energy particle physics, were hoping to describe what they consider to be the real world in terms of supersymmetric particles. So supersymmetry is to do with Bott symmetry, and fundamentally this contains the octonions as an unavoidable component. Yes? So I told you when we were working with A4 here, when I chopped off, when I was thinking of A4 as a sub diagram of E6, I got G5, GL5, so the 5 by 5 matrix. So that's not in the least bit difficult. Here we get SO8. So all of the even orthogonal groups have spinor double covers. This one has two completely different spinor double covers. Yes? So, if you take D4, then it's a lattice, and when you when you take the root lattice of D4, it's a positive definite range 4 matrix, and it has a dual matrix, the matrix of linear forms. And the quadratic form of D4, which you can draw directly, has determinant 4. And that means that when you include D4 into its dual lattice, you get a lattice of co-index 4 lying over it. That's true for all the DNs, yeah? But here, when n is even, you get the root of order 4 is this. If you want, if you've got a piece of paper handy, draw the two-dimensional square. You will notice that its vertices form a bipartite graph. Now draw a three-dimensional cube. You'll notice that instead of that bipartite structure, it's it's not bipartite, because if you start coloring white and black, you'll eventually get to the antipode, and the antipode is 3 steps away. I'm just saying, the groups, the orthogonal groups corresponding to D2n and to D2n plus 1 have a completely different nature. The Clifford algebra the spinor structure of them are different. Yes, and this VID4 is even crazier than that. So in this case, so the Dayton diagram itself, it's drawn like that because, for typographical reasons. I can't draw in plain text. I can't draw something with angles of 120 degrees. But as a graph, that has S3 symmetry. The three branches are completely different. Yes? And if I take all of these spin double covers, I get a covering which is Z2 plus Z2 covering of the roof, a central extension, and Z2 plus Z3 also has threefold symmetry, right? The three vertices 0, 1, 1, 0 and 1, 1 are permuted by an automorphism. Yes? Now, the homogeneous spaces for an algebraic group, the biggest homogeneous spaces are what happens if you delete one vertex, right? And SO8 as written is a quadratic form in 8 variables. So I can set quadratic form equals 0 and take proj of that. I get a non-singular 6-dimensional quadrate here. And I get, if I look at 4-dimensional isotropic subspaces of a 8 space, that means the 4 vectors spanning it are length 0 according to this indefinite quadratic form and orthogonal to each other, then I get 2 components. So these are the 2 spinor components. So I have 3 varieties here, and they are all 3 of them, 3 projective homogeneous spaces for SO8. They're isomorphic, but the isomorphisms are not linear. The way to think about them, if you read John Byers, is write down a trilinear form in 3 sets of four variables, and then you can think of that in different ways as the octonion, right? So if you want to understand this problem, you may be able to find the 2 spinor components. 2 spinor components are different. They're embedded in different spinor spaces. They are isomorphic though, so it's, and possibly you can do something sensible with those isomorphisms. But if you want to treat the 3 of these on an equal basis, you have to use octonion algebra. Right. So, at some point in the future, I will be able to write a textbook that says how to do octonion algebras in an easy way, in a way that I consider to be adequate. Yes, but at the moment, I hope to be able to do. Yeah, so let me go on now to other things. This is, to my mind, possibly the biggest problem. Yes. So when I, you know, I mean, if you're an algebraist, you know how to look up the dimensions of all of these groups and the dimension of their singular locus, right? So, and their homogeneous spaces and their representations. So G2, the algebraic group G2 is described casually as the symmetry group of the algebra of octonions. Yes, so if you're a pure algebraist, this makes sense to you. But if you want to understand it's a human being, it's quite complicated. So saying that it's a symmetry group does not provide any elements in G2. So, you know, the combinatorics of G2 has, I haven't got it written down for you, but you can look it up in Wikipedia. You get, it has this thing which is a regular star of David in a pentagon. And it has the root system has long vectors, long roots that go out to the points of the star, and then it has short roots that go to the inner. So there are 12 roots there. The symmetry group of it is the root Z12. Yes. So the method the algebraist will tell you is G2 has a 2 in it, which means that the maximal torus, the thing you think of as the diagonal elements down the matrix algebra, is 2-dimensional, right? And then there are these 18 roots. So this is 20-dimensional. And it's got one 7-dimensional representation and one 20-dimensional representation. The 7-dimensional representation is it acts on the imaginary octonions. Yeah. So you know the octonian. You've heard of the octonian algebra as an 8-dimensional algebra over the reals. But I'm an algebraic geometer, so everything for me is over the complexes. So most of the time, something which I know how to do over the complexes, you'll take away and try to do it over the reals and find you can do it in 5 different ways. Yes? So if you write down the equation of the circle, it's x squared plus y squared plus z squared. Sorry, x squared plus y squared equals 1. But if you write x squared plus y squared equals minus 1, you get an algebraic variety whose real points are not very interesting. Yes. So I want to construct G2 together with subgroups in it that generate it from the root system. So every algebraist who's ever given a lecture course on Lie algebra would have taught Sayre's theorem, which says that you take the maximal torus and you take any of the roots. So the roots is something that gives you a reflection. Then you can use that to cobble together a subalgebra of the Lie algebra, which is SL2. So, we write H, X, and Y, and we think of H as being the diagonal matrix 1 by 1. You take X as being the upper triangular and Y as being the lower triangular elementary matrix. And as Lie algebras, as elements of the Lie algebra automorphisms of 2 by 2 space, you get a Lie algebra that is isomorphic to the Lie algebra for SL2. Now, everything, Lie algebra is a kind of microscopic view of a Lie group, and so I want to lift Sayre's theorem up to the Lie group. And G2 is, in some ways the simplest exceptional group there is. Yes. Anyway, I say I want to catch G2 by going down to D4 first. Yeah. So I gave you the linking diagram of D4. It's one central vertex and 3 other vertices that stick out. You should draw it with angles of 120 degrees. Then you can do a 3-fold rotation there. Yes. And you get the linking diagram of G2. You get one short vector and one long vector and 3 arrows drawn together, drawn along the same line, going from the short route to the long route. Yeah. So let me continue. This is my last slide. If you want me to continue talking, I'll go into computer algebra. Yes. So by doing this, I'm telling you how to do. I want to tell you in principle that there should be a method of constructing every simple Lie group. Yes, so the Lie groups and things with these names, I've given you A, there's D's, there's B's and C's, but they're really very simple structures compared to these things. Yeah, and then these exceptional groups, E6, E7, E8, and F4 and G2. Yes, so the D2n plus 1 corresponds to this group, SO4n plus 2. So you just draw matrix in square block form for 2n plus 1 by 2n plus 1, 4 blocks of 2n plus 1 by 2n plus 1. And you write exactly as I did before, 0, 1, 1, 0 in the 4 places. Yeah, so that's the standard quadratic form in 4n plus 2 dimensions. And so there's a group there. It's just very simply the group of orthonormal matrices with determinant 1. Yes, and you can define that over the reals, but I want to keep it over the complexes. Yes, now that group has a spin double cover. So, it's the same spin that you know from quantum mechanics of the electron or from the Dirac equations. And anyway, let me just let me move on. It has this double cover. It has 2 spinor spaces, which are the homogeneous projective homogeneous spaces, right? And so, they're 2 slightly different things, but they're only really to do with whether you're thinking of the top or the bottom of this 0110 medium point. Yes. So, if you're over the reals, then of course you're going to have a different time. Yes. So D2N, my problem with triality is that when you do D2N, the 2 components of the Clifford algebra have to be treated in different ways. So you can't really think of these things as being just a very simple-minded linear change of coordinates in the variable. So, I think there are some triality issues that persist, right? It's, of course, not the threefold symmetry aspect, but the aspect that the 2 parts, the 2 direct summands of the Clifford algebra cannot be written in the same form in the same coordinate system. Right, now E7. So I told you cubic surface. Algebraic geometers love the cubic surface. It's easy enough to set as a problem for undergraduate students. It has these 27 lines with their really beautiful classical symmetry. Now, at some point, you learn that the cubic surface has on it 6 disjoint lines, and you can contract these to non-singular points, so you can make a morphism of algebraic surfaces that take those lines to points on a non-singular surface and don't do anything at all outside, map the whole of the rest of the surface isomorphic. Yes. And then you say the cubic surface is what you get if you take P2 and 6 points in P2 and blow up those P2. So blowing up means you take a point of P2 and you replace it by a neighborhood of the projective line to its tangent space. Yes, so if I had a blackboard, you can do this on a piece of paper. Take a piece of paper, draw a point, draw X and Y coordinates passing through it, and then draw a bunch of lines passing through the origin. They go like this. Yes? Now, those lines all meet in the origin, but I could take the disjoint union of all those lines. So that replaces the single origin with a kind of cylinder-like structure with here are the points on the lines that only have one point in the plane. That's what a contraction is. Yes? So in any case, if instead of 6 points, you blow up 7 points, you get del pezzo 2. So del pezzo 2 still has this property that algebraic geometers love, at least modern algebraic geometers love. It is a Fano variety. It has minus k ample. Yeah? And it has a configuration of 56 lines. And, I told you how to write the configuration of lines on the cubic surface using that Schliffli double six. So, this configuration of 56 lines is more complicated. So, one issue is that there are lines that meet other lines in 2 points. But they look like that. Instead of 2 lines meeting at a point and that's all there is, there's one line and another line, and they meet in 2 different points. Right, that's because the canonical bundle is ample, but it's not very ample. Technical term. Instead of, the canonical class here is the thing I called that characteristic vector when I was talking about lattices. If you take cubics in the plane and you impose 7 points in the plane as a base load. So cubics in the plane is a 10-dimensional vector space. Imposing 7 fixed points cuts that down to 2-dimensional. So you get 2 algebraically independent ratios of cubic form. And they give you a map from the plane, the original plane that you were blowing up, to another plane, and that map is 2 to 1. And the double cover of the plane branched in a quartic curve is this thing, is this dp2. And the quartic curve has 28 bitangents. And each bitangent lifts the 2 lines like this on the surface. Yes? In any case, we get those 56 lines and we put them into a configuration geometry in the same way as I did with the lines of S3. The lattice that these live in is a Lorentz 8-dimensional lattice with 1 plus dimension, so 1 time direction, and 7 minus direction. Yes? And the root system is the orthogonal complement of the it's the orthogonal complement. So let me see if I can do this in computer. So it's slightly too big to do quickly. I'll show you quickly how I generated the two lines. Can you see this screen? Computer algebra, as I'm moving about?
Yes, I can see it.
Okay. So I've got vectors. This is for the cubic surface. So I told you I'm taking 7-dimensional Lorentz lattice. So there's x squared, and then there's minus sum of y squared, right, for as many as there are here. So this means that there's a quadratic form there, which is 7 by 7 diagonal matrix, 1 and then minus 6 times. Yeah, and this is my characteristic vector. Characteristic means that when I do k dot product with any vector in the lattice, I get an integer which is congruent modulo 2 to that vector squared. So it's simplest to do this. Let me, just not to spoil the experience for you. These are the lines of the cubic surface. So these are the 6 points of P2 that I blow up, and these are the 15 lines, Mij, passing through 2 points. Yes? So you can see that, and then at the end, oh dear, 2, 4, 5, 2, I have to put another one here. Let me, just making it simpler for the computer. Okay, I hope that works. Yeah, okay. So I did something illegal. Okay, so it's this is, you know, when you, if you imagine we use it, then this an error occurred. It's sort of basically comforting. It tells you you're still online and so on. So, you know, this was my, this was the table I gave you when I was talking about double sixing. Yes, here are 6 disjoint lines on the cubic surface. Here are 15 lines that meet. 5 of them meet L1, 5 of them meet L2, and so on. And then here are the other side of these are the 6 Nij, the other side of the Schliffli double six. Yes? And then I'm going to ask the same question for the roots, but I'm going to ask it in a slightly more grammatical fashion. Okay, so the area, so the error was I defined this dot product to be a function of whatever you put there. And the function assumes implicitly that both AI and BI have the same number of entries. And okay, so now let's ask who the roots are. And it will tell me, I think, 60. I'll ask number of roots. When you do computer algebra, it very often happens that you never want to see the output, but you do want to see the number of outputs. So this means that the Lie algebra, the root system of E6 has 36 positive roots and 36 negative roots. And that's just how root systems work. Yeah. And 72 by coincidence. So, I can do the same for, let me stop doing this because it's not so interesting. Yeah. So I'm back to my, so, I believe that, some of what I believe is because it's already established fact in the mathematical literature. So these homogeneous symmetric spaces, homogeneous projective spaces are known to exist and are not particularly different. Yes? My point is that I want to make them in a way that I personally am capable of understanding. Right? If I can understand it, then probably lots of ordinary human beings can understand it as well. Whereas, the abstract algebraists have a completely different point of view, that algebra must be rigorous, even if nobody has any idea what it means. Yeah. So this group here, I told you how many roots E6 has. I haven't told you how many roots E8 has, E7 has. I think it's probably 100 or something like this. Right, and then E8 is really very complicated. And the routine I told you to calculate the roots, if you only ask the question once, then Magma will tolerate you asking it. For E8, it just won't work. You have to use a bigger computer. Yes. So that's the end of the talk. I'm very grateful to the audience for keeping me company.